Okay, so hi everyone. My name is Lohit Kal. I am from Indian Institute of Technology, Bombay, and today we will do the week some mathematics of week 3. So let's start. So just a moment.
Hello, sir.
Yes.
Sir, actually, in assignment 3, there is a problem. Question number 8. Here, two options are same. Question number option A and option C both are same, and both are correct answer. Here, I have chosen options A, but system has taken option C, so that
Yeah,
I got the negative 0 marks. So, what
uh,
can I do?
actually, I do not. I do not look after those assignments, so you can mail them or write in the Google group, something like that. So
Sir, I can share the screen so that.
no, actually you may be right, but I do not look after those assignments. That is the thing.
Sir, it is dates over is already.
Yes, I understand, but I am not the TA for the course. I will just conduct live session. So those two
So,
are
so,
the different
can
things.
you suggest me? So, what can I do now?
Mm, contact the NPTEL team or the person assigned to the groups. I mean, person assigned to the course. You probably have some mail ID or Google groups, something like that. You can write it there.
Okay, okay. Okay, thank you, sir. Thanks so much.
Okay, so let me share my screen. Okay, so I will, I will come to question one. I will come to first few question a little later. So let's solve few simpler problem. Then I will go and discuss about all these things. Okay, so first let's start with question 4. So suppose you are given a nonlinear function which is gx equal to x square minus 297. Okay, and and you need to find what will be the formula of x using the Newton-Raphson technique. You need to find the formula for xn plus 1. So there are four options. Option A is xn plus 1 equal to 0.5 xn minus 297 by xn. Similarly, xn plus 1 into 0.5 into xn plus 297 by xn. And this is the third option, and D is the none of the above. So take a few minutes, and this is a very easy problem. So take a few minutes, and you can write the correct answer in the chat box, and then I will start discussing. So this is the formula for the Newton-Raphson method. You just need to put it here and simplify it. Are you getting this answer? 0.5 into xn plus 297 by xn. So if you are getting this answer, then this is the correct option. Then your option B, option B is will be the correct choice for this question. Now question 5. So which of the statements below regarding the convergence of the bisection method is true? So the option, the S1 is, statement 1 is the iteration is always guaranteed to converge, and option B is the order of the convergence is linear. Okay, so in the bisection method, if we have a function like this, so in the last class I also showed a code to how to solve this kind of problem. So you need to find 2 points to initial guess. This is probably A, this is probably B, and if B is less than 0, then you just reduce the error by 2 and then do the same thing, and all continuously checking this factor fa into fb has to be less than 0. If you are doing like this, then you are guaranteed to reach a solution. Okay, so this option S1 is correct. The iteration is always guaranteed to converge only when if you find two initial choice correctly. If your function is like this, if it never crosses the 0 point, then you will not be able to find anything like that. So if this condition is satisfied, then then the iteration is guaranteed to converge. But this convergence procedure is slow because here en plus 1 equal to some constant into en, because we are reducing the gap, we are reducing this distance. My next choice will be m equal to half into a plus b. So so maybe, sorry, the middle point may be somewhere around here. So it's maybe somewhere around here. So I reduce the error by half. Okay. So this is a linear convergence procedure. Here en plus 1 is the error at the n plus 1 step. C is some arbitrary constant into en, or error at the n step. So this is a linear convergence procedure. So S1 is also correct. So both are, option D is the correct choice. Okay. Now another logical question. So Newton-Raphson method solution numerical equation y equal to fx is not preferred when graph of fx is vertical, graph of fx is not parallel, graph of fx is a straight line, graph of x is nearly horizontal where it crosses the x-axis. So in case of the, so let's first go with the formula. So what is the formula for the Newton-Raphson technique? It is xn plus 1 equals xn minus f of xn by f prime of xn. Okay. Now at the root, if this value is 0, okay, then these things become infinite. Then we will not be able to find any root in that case. So graphically, suppose I have a solution like this, some function like this, okay, and sorry, let me draw it properly. there is a flat line around this x equal to 0. Okay, it indicates that here, suppose this value is alpha, if alpha equal to 0, similarly f prime of alpha is also equal to 0. Okay, so that means at this point, here my f prime of alpha equal to 0. So this is nearly horizontal where it crosses the x-axis. Okay, so it indicates that this f of alpha by f prime of alpha, this thing cannot exist here. Okay, because it will be, this is some quantity by 0, so these things will be infinite. So in that case, we will not be able to solve the Newton-Raphson technique using this formula. So Newton-Raphson solution is preferred when is not desired for this kind of solution. So option D here is the correct choice. Now, another question regarding the Newton-Raphson technique. So among all those techniques you have learned, regular fallacy, secant method, bisection method, Newton-Raphson is the most powerful method. Here you just need one initial guess and you will be able to solve the problem. But here the solution is not guaranteed because it depends on your initial. It depends on your initial condition, initial guess. If you take your guess correctly, if the function is well, then you will get a converged solution for that. Now, which of the following form of equation you can apply the Newton-Raphson technique? The option A is the algebraic equation only. Option B is the transcendental equation. Option C is both of them, and option D is none of those. Okay, so just a second. So what is algebraic equation? Algebraic equation is anything we do. Suppose x cube minus 3x square plus x equal to 0. So Newton-Raphson technique is very powerful solving this kind of problem. Okay, and similarly it can also solve the transcendental equations as well. So here, so which of the option will be correct? So option C, that both algebraic and transcendental equation is the correct choice. Now, so we will be solving many problems regarding the. I will talk about this, the fixed point iteration method, and I will show you a new technique to visualize the convergence. So those things were in the question 1 and question 2. I will come to that. So first, so how to represent a transcend sorry how to yeah so this is the equation of the transcendental equation. Okay, so cos x minus x. So Newton-Raphson technique can very easily solve this kind of problem. Okay, so now for the fixed point iteration case, how we represent it? This is xn plus 1 equal to f of xn. Okay, and sorry, yeah, f of xn, and the solution the solution is the solution will converge when if x star equal to alpha. Here alpha is the root. If mod of f prime alpha is less than 1, then the solution will converge. So this is the criteria for that. So we will use this criteria and solve many problems. So just hold on with me. So first, so here in this question, so how can we represent these things? Cos x equal to x. So this can be representation xn plus 1 equal to cos of xn. This can be one kind of representation in this process, in the fixed point iteration technique. Also, we can represent it in this manner. So cos x equal to x. This implies x equal to cos inverse of x. That means xn plus 1 equal to cos inverse of xn. So this can be another solution. So here this option A and C. So these two are the correct choices. Okay. All right. Now calculate the approximated value of x until 6 iteration for x cube minus 4x plus n in the interval of -3 -2. So I have done it for many iterations, not only 6, just to show you how you can get a result. So in the last class I have also talked about this code. So I will talk about it again. So here this is your function fx equal to x cube minus 4x plus 9. So these two are your initial guess, a equal to -3, b equal to -2. So these two are given in the question. So the first choice is obviously 0.5 into a plus b. You should always verify if b is less than 0. If this is satisfied, only then you can go to uh, this uh, this process m equal to half of a plus b. If this is not true, then you need to change your initial guess and redo this. So I am taking my max seed. Max seed is the number of maximum iteration is 100, and my tolerance is 1e minus 4. Like I have told in the last class that this you if you're not satisfied with this, increase the tolerance level. That means make it 1e minus 6, 1e minus 8, according to your problem. So converts. This is my initial. So this is my initial convergence. I am taking some arbitrary value 1. You can take 2, 3,000, anything. And it is my number of iteration, my count of iteration. So I am starting with 1. So when this condition is satisfied, when this conf is greater than tol, I mean tol is 1e minus 4, my tolerance level, and conf is my convergence. If it is greater than this, and if the number of iteration is not less than the maximum iteration number, which is 100, then I will do this. If fa into fm is less than 0, then substitute m with b. Okay. And if fb into fm less than 0, then substitute m with a. Sorry, substitute then do this substitution, and again do this process. Okay. Now I want to find my root. So the absolute, so my function is x cube minus 4x plus 9. Result is 0, and from this process I will get some value of fm. Okay. So my error is f of m minus 0. 0 is coming from this. Okay. So and I am taking the absolute value of it. So and it equal to it plus 1. I am increasing my iteration count. So at the end, if my convergence is greater than my tolerance, so if it is not that means if it didn't converge up till this 100 iteration process, then printf that no root is available, and otherwise just print this. This is the value of the root. Root is minus 2.7. Iteration is number of iteration count, which is coming from here it. So maximum number of iteration is 16, and here this is the conversion. This is 4 into 10 to the power minus 6, and which is less than 1e minus 4, which is my desired tolerance tol. So you are getting, so this solution is minus 2.7 something. So here it was required up till 6 iteration. So I extend it to 16 iteration because you are just doing simple coding. So you can increase it as you wish. So option C is the correct choice. Okay, so just let me stop recording and restart it. Just a second. So this is another question. So to find the root of a function, it is defined at 2 points -1 and 3 as f -1 equal to 7 and f3 equal to 10. Now the question is it sufficient to use the bisection method? The answer is false. Because to use the bisection method, we must have fa, fb less than 0. Another question can we use regular falsi method here? The answer is still no. For the regular falsi method also we need this condition to be satisfied, but here we can use the secant method, because for the secant method the initial guess can be at the same side of the function, not on the opposite side of the root. So for this question, for the bisection method, we cannot use this thing. So this for this value f -1 equal to 7, f3 equal to 10. Here if we multiply it, it is 70. So 70 is greater than 0. So we cannot apply it here. Now let's solve another questions. Just a second. So I haven't written it. I have not written the question, but I will tell you what it is. You can note down the question if you wish. So the question is this is question. This will be question number 11, right? The question is the minimum number of iterations needed to evaluate square root of 28 up to 3 decimal places using NR, Newton-Raphson, and with x0 equal to 5. Okay, so this is the question. So the answer is very straightforward. We already know the formula for it. We already know the formula. The formula is xn plus 1. So it will come. The question is just similar to this. The question is exactly similar to this. How? So here I need to find the root of 28. Okay. So what will be the my desired function? Well, my function will be x square minus square root of 28. So this is my fx. Because at x equal to square root of 28, this is my desired root. Okay, this value will be 0. So I am taking my function as fx equal to x square minus 28. So if I if I plug in the formula, we have already solved it in the fourth question. So xn plus 1 will be 0.5 xn plus 28 by xn. So here you have x0 equal to 5. We know that 5 square equal to 25. So it is close to 28. So the initial guess is good. So x1 will be 0.5 into 5 plus 28 by 5. So what will be the solution? Let's just do it. So 0.5 multiplied by 5 plus 5.6. So x1 is 5.3. Now my next guess is, so this is 5.300. Okay, because I need the correct answer up to the 3 decimal places. Here x2 will be 0 0.5, 5.3 plus 28 by 5.3. So this 0.5 into 5.3 plus 28 by 5.3. So it is 5.2915. That's something. Again x3 is 0 0.5, 5.2915 plus 28 by 5.2915. This answer will be plus, yeah, so it is again 5.2915 dot something. So here first three digits are satisfied, so we can stop at the second iteration. So the number, so the minimum number of iteration required will be equal to 2. So we need minimum number of 2 iterations to find the root of the square root of 28. Sorry, to find a value of square root of 28. All right. So let's solve another problem on the Newton-Raphson technique. Uh, just a second. Let me just find the question. Yes. So the question is, again just similar to the last problem. This will be question number 12. So you need to find the root of square root of 17. Okay, you need to find the answer. So here it is provided that en equal to square root of 17 minus xn. This is the error. Okay, at the in its state. So 4 options are given. You need to find what is the correct answer. The option A is en plus 1 equal to en by 2xn square. Option B, en plus 1 equal to minus of square root of 17 en square by 2xn. Option C is en plus 1 equal to en square by square root of 17. Option D is en plus 1 equal to minus en square by 2xn. Alright, so let's just proceed with this. So I need to find the value of en plus 1. Okay, so in all the options my left hand side is same. So I need to anyway go to en plus 1, and en plus 1 is square root of 17 minus of xn plus 1. And we know what is xn plus 1. Xn plus 1 is from the xn plus 17 by xn. Okay, again in this case my f of x is equal to x square minus 17. So if I substitute this here, it will be en plus 1 equals square root of 17 minus half xn plus 17 by xn. Okay, so let's simplify it a bit. 17 minus half xn square plus 17 by xn. Now I am provided that en equal to square root 7 minus xn. This means I can write that xn equal to, square root 17. 17 minus en. So xn square. equal to 17 plus en square minus 2 square root of 17 en. Now I will substitute this in place of this. So en plus 1. So okay, so let me just copy with this thing. Copy, paste. So this is my en plus 1. So I will substitute it here. So it will be square root of 17 minus half into I think I have made, did I made a mistake somewhere? Hmm, just a second. It will be 17 plus en square minus 2 square root of 17 en by xn. Square equal to 17 plus en square. I am no, sorry, en square. Just a second. Huh? So this is correct. So it so xn plus 1 equal to xn minus f of xn by f prime of xn equal to xn minus xn square minus 17 by 2xn. It will be xn 2xn square minus xn square plus 17 by 2xn. Yeah, so this is correct. Half of xn plus 17 by xn. Yeah, so this is correct. Yeah, so by minus 17. Right. Let's not do in this manner. So it can be made simpler. So minus half. This is xn plus 17 by xn. Okay. So in place of xn, substitute this. So then it will be square root of 17 minus half square root of 17 minus en plus 17 by xn. Okay. Right. 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 Now in place of xn, I am substituting en, because in the numerator, in all those options, I don't have any xn in the numerator. Okay, I have xn in the denominator, and the numerator I have en, so I will substitute accordingly. So in place of xn, I am substituting root over 17 minus en, because remember, en equal to square root of 17 minus xn. So it is again plus 17 minus, in place of xn, write square root of 17 minus en into en by xn. So equal to half 17 n 17 en plus en square by xn. So we have got half en square minus 2 square root of 17 en plus 17 plus 17 by xn. So this result is, so this is en minus square root of 17 whole square. Uh, just a second. Yeah, I am probably making some mistake in this. Just a second. Just give me some moment. I will solve it at the end. So let's move on to the next part. That so so here, so suppose you see here, we will check the rate of convergence for various methods. So here I have tested it for the Newton-Raphson method and the bisection method. So remember that there was a, during the lecture, so you are provided with the formula. So how to determine the rate of the rate. Suppose your en plus 1 equal to some constant into c into en to the power p, then what will be the value of the p based on different method. So you are provided with, so you will find this, that it will be log of en plus 1 by en by divided by log of en by en minus 1. Okay, so this will be your formula. Now, so what I have done, that I have considered this function x to the power 16 minus 1. This is your fx. Okay, so this is the value of your fx. Now, so here this first method is the Newton-Raphson technique. So what I have done here, small n is my maximum number of iteration, n equal to 500. This is my maximum number of iteration. So here the code is very simple. So here x equal to, just I am writing down the formula, x equal, So I'm writing down this formula xn plus 1 equal to xn minus x to the power 16 minus 1 by 16 into x to the power 15. I have just written it down. X equal to x minus x to the power 16 minus 1 by 16 into x to the power 15. At each iteration step, the value of x will be updated. Okay. And here E of I is 1 minus x. Here what is 1? 1 is the exact root of the solution, and 1 minus x is the estimation of error. So and after that I am putting this value. Remember that here my I range of I, you have to modify it a little, because I the because here it I goes from 1 to 500, and in the formula you have I minus 1 and I plus 1, so it cannot start from 0 and it cannot go beyond 500. That means it cannot go up to 501. So in that way I have modified my I accordingly, and here this is the formula for that. So here the m will be 1 to 498, and I have plotted it. And we all know for the Newton-Raphson case, in the Newton-Raphson case, the solution will be the rate will be 2. Here the rate will be 2, and here this is the corresponding plot. So here this is P. This is my number. This is my number of iteration n, and you will find that it goes. The rate was initially small, but as the number of iteration increases, it reaches the value 2. Okay. Now this is an asymptotic expression. That means it is for the Newton-Raphson method, P will be 2 when limit n tends to 0, P, that is the value of 2. Here the n tends to infinity, reaches around 100. This is probably 112. Okay, around that point it reaches the value 2 and it stops there. Okay, so in this case you can very easily verify the rate of convergence for this method. Similarly, you can do it for the bisection method. So again, this is for the same thing, s to the power 16 minus 1. Here these two are the two initial guess. A is 0.3, B is 2.7, because when x is so 0.3 to the power 16 minus 1, it is less than 0, and 2.7 to the power 16 minus 1 is greater than 0. So this initial condition is satisfied. So this is my first initial guess. E of 1 is, so I have also taken the first P1. This is first error, this is E of 1. And I am taking here my maximum error is 40. I have given tolerance, but I have not used it. So while IT is less than of max IT, then exactly the same code, the same one I showed a moment before. So I will not go through it. I will not go through it again. So after that, I am putting this P. Okay. Now here I am plotting down the result, and we know for the bisection method the error en plus 1 equal to some half of en. It will be so the order is 1, and you can see here very easily that after some jump, the value gets fixed at x equal at this is here we can find the value of p equal to 1. Again, in this case, the limit n tends to infinity, ln en plus 1 by en by en minus 1 will be 1 only when n is sufficiently large. Okay, you can see from the code that initially the rate is not 1. Okay, there is some jump, then it grows, and after that after that the value is fixed at n equal to 1. You can similarly find it for the second method. Just do that. Just you have to just need to modify the body of the program. Then the rest of the part will be same, and you can find the rate of convergence of your second method. Okay, so yeah, please try this method, and please modify the code accordingly for the second method. I haven't done the second method here, but the exact idea is exactly the same. You just need to have some large number of iteration, this is the iteration count, and you just run it inside the loop. then after that you will find that you are getting this kind of plot. Okay. All right. Okay, so now I will talk about no. So now I will talk about a new thing, not exactly the new thing. Now we'll talk about the fixed point iteration method. So here, like I told that you're also told in the class that when the modular, when the absolute value of the slope at the root, if it is greater than 1, then the solution will not converge, and if it is less than 1, then the solution will converge. Okay, now we will implement this idea. Yeah, we'll implement this idea graphically. So how we can modify it graphically? So I will to talk about few new things in the code, and you can I will share the code with you, and you can modify it. So let me just share my screen again, just a moment. So let me first start the recording again. Okay, so let's share my screen again. Just a moment, my internet is a little slow. Yeah. So so let's solve that problem, like what I was trying to do and making mistakes. So let's solve that again. Okay, so here instead of says the same question, so also the options are same. So instead of just 17, here this is just option, this is 7, same thing. So this is the formula for the thing, and this is the value of the xn plus 1. And similarly, in the place of en plus 1, just substitute, in place of the xn plus 1, substitute this like the last time. So probably I have done in some silly mistake over there, and if you just multiply it, it will be xn plus xn square minus 1 2 square root 7 xn plus 7. Okay, and this thing will be it will be equal to minus of xn minus square root of 7 whole square by 2xn. And you are provided that your, so in that problem it will be square root of 17. So I will refresh it and send it to you. So in this case it will be just xn minus square root of 17. So it is just minus of en square by 2xn. So this will be a solution. Okay, so let me go to that note. So let me just refresh this. So here it will be xn plus 1 equal to half of xn plus 17 by xn. So it will be half of xn plus 1 plus 17 by xn, and your en plus 1 will be square root of 17 minus xn square plus 17 by 2xn. So I made a mistake that substituting xn square here with en and makes the problem complicated. So if I just multiply it, I will get 2xn square root of 17 minus xn square minus 17 by 2xn. So it will be minus of xn minus square root of 17 whole square by 2xn, and that is minus en square by 2xn. So your this option is correct, minus en square by 2xn. Okay. Okay. Now let's move on to the new thing. So here your function is xn plus 1 equal to r into xn into 1 minus xn. So this is a very interesting function. Okay, this it looks very simple, but this is very interesting. So if just search logistic map in Google, and you will find all the related documents, all the interesting document related to it. I will talk about some interesting facts about this function. So this is a very simple function. If I just plot it, xn plus 1 versus xn, it will be simple parabolic curve. Simple. Okay. Here r is unknown. R can be anything. R can be of any value. Okay. So here I have provided some options, and first we need to check. First we need to check the convergence criteria of this function. Okay. So let's see that. So first we need to find the root of the function. So this is my fx equal to r into x minus of x square. Okay. So f prime of, so its root are x equal, so, and this is y equal to x function. So I need to find the root at this point. I don't need the root, I need the slope at this point. Okay. So my, suppose this is my phi of x r, and if I want to find the value, it will be r into x into 1 minus x minus x equal to 0. So solving this quadratic equation, I will be able to find root. Okay, so let's try that. So it will be minus rx square plus rx minus x equal to 0. So x equal to 0 is one root always. Okay, so just we are not interested in x equal to 0 so far. So let's figure. So this is one root. Just keep it. So it will be minus rx plus r minus 1 equal to 0. This implies rx equal to r minus 1. So x equal to 1 minus of 1 over r. So this x star equal to 1 minus of 1 over r. This is my one root, and this x star equal to 0 is another root. Now this solution will converge. Now the sorry, not solution, the iteration technique will converge if I have a function of the kind of xn plus 1 equal to phi of xn, right? If mod of f prime of alpha, or sorry, f prime of x star is less than 1, then the solution will converge. So this is the criteria. Now, so we have already found our two roots. One is x equal to 0 and one is 1 minus 1 over r. So here my phi of x, sorry, so phi of x is already written. Now I need to find a phi prime of x. So this is phi prime of x. It will be r into 1 minus of 2x. So the phi prime, so I have two roots. Let's write down the two roots over here, do it properly. Let's use another color, red. So one root, so x for x star equal to 0. My phi prime of 0 is just r. Okay. So this is my one root for x star equal to 0. And for x star equal to 1 minus 1 over r. So my phi prime 1 minus 1 over r is equal to r into 1 minus 2 into 1 minus of 1 by r. So it is r into 1 minus 2 is minus 1 plus 2 by r. So the value is 2 minus r. Okay. Now this result is very interesting. Why? You will find it in a moment. So I have two values of slope. One is r and another is 2 minus r. Okay. So now when r is less than 1, what will be so for which of so if I use this method, then my solution will converge to which root? So let's check. So the first choice is r equal to 0.8. Okay. Now for r equal to 0.8, this value is less than 1, but this is greater than 1. So if I use the solution technique, this fixed point iteration technique, my solution should converge to this root. Should converge to x star equal to 0, not x star equal to 1 minus 1 over r. Right? Now for r equal to 1.7, this value is greater than 0, but this is less than 0. Hmm? There it will converge. There in that case it will converge to this root. Now here comes the interesting thing. When r is greater than 2, then we will not, then this is less than 0 and this is less than, no, for r is greater than 2, again the same thing will happen. Now when r is greater than 2, then this is obviously greater, this is not a stable point, but it is less than 0. Okay. Similarly, when r is 3.2, 3.8, this is obviously greater than 0, so the solution will not converge to this, but this is less than 0. So after it hits, so after r greater than 2, something very interesting happens in this case. Okay, and you will see that in a moment. So we can only validate it till r for this function. For this function, we can only validate it up to few values of r, and after that we don't have any clue what is happening. So in that case, we need to, this function, they have various interesting properties. If you just google it, you will be able to find, and you will find that what will happen in the case of r 3.2 and 3.8. Now I have developed a code so for all this R, and you will see that using this code how we can find how we can be able to find the convergence criteria. Now, so just first let me give a brief theory of that. So my function is xn plus 1 equal to phi of xn. So this is my function. So just what is happening in this function? So this is my xn plus the straight line, 45-degree line, and this is my some function. It may not be this function, this is some arbitrary function. This function is phi of xn, and this is xn plus 1. So what is happening? So suppose I am at xn plus, so I am use a different color. So I am at xn plus 1. Okay, so this is xn. Phi of xn means I will straight go to this point. And at the same height I will get a xn plus 1. So this point will be my xn plus 1. Okay. Now at this xn plus 1, I will come back to again phi. So this is my phi of xn plus 1. And what is phi of xn plus 1? It is xn plus 2. So again I will move horizontally to this point. This is xn plus 2, right? So this is xn plus 2. Now again from xn plus 2, I will move to the curve. It will give me phi of xn plus 2. Similarly, if I move to this thing, it will give me xn plus 3. Similarly, if I this will be my xn plus 4. Similarly, it will just rotate something like this, and it will either converge or it will diverge. You will see in a moment. So this is the basic idea of the code. So this is what this formula is telling me. I will start from a xn, it will go to the phi xn. Correspondingly, I will be able to find xn plus 1. Then I will able to find phi xn plus 1. It will give me xn plus 2, and so on. So I will check for this initial value r equal to 0.8. 7 is there. Oh, yeah, I made a mistake. Okay. So I made a mistake. Here is saying, so this limit is not r greater than 2. Okay, it will be r greater than 3, because the criteria says the absolute value of phi prime x star should be less than 1. The absolute value, not the normal value. Okay, so when r lies between 3 to 1, sorry, so when, yeah, so it lies between 3 to 1, then the solution will converge to this point, 1 minus 1 over r. But when it goes beyond 3, then we cannot find using this criteria the it will be a stable point, because at that point modulus of phi prime alpha is greater than. So that means it will not converge to this point. It is telling me this. So when r is greater than 3, phi prime of x star modulus of absolute value of phi prime of x star is greater than that. So it will not converge to it will not converge to this root. Okay, either way it will not converge to this zero root. So there may be some other roots present in the system, so it will go there. So when I show you the code, then you will understand what is happening. So let's start with that. So we can be so when r is less than 3, less than 0, so in this case we can very easily, from the theory we can very easily understand what is happening. Okay, but beyond 3 it is not quite trivial. So here I have to start somewhere. This is my x0. This x0 is 0.8. This is my value of this is my value of r. It is again 0.8. I am considering this. C, you do not need to consider c, some arbitrary thing. I haven't used it in my code. So here g and vv are some two. I have initialized to vector, and I will later modify it. Here my func is, this is my, I am defining the function over here, r times x times 1 minus x. So f equal to func of x0. This is, so I am finding the value of function, my function at x0. this is my tolerance level maximum iteration thing, same conf, and I am defined some for this two are for the plotting case. So here in the Vx I am storing the value of x, and here Vf I am storing the value of my functions. Okay, here I am using again the same criteria like in the inside a while loop. Here this is my definition of the tolerance here. Previously I was using my convergence based on the function. Here I am defining my convergence based on my value. So x1 minus x0. So the next iteration minus previous iteration. This is my convergence criteria here. So here I am doing this thing, and finally defining that x1 equal to f. Okay, so this is from the xn plus 1 equal to phi of xn. So it is coming from this fact. Okay, and iteration is iter equal to 1 and doing this thing. And this is the value of vv. Therefore, I am storing I am defining uh, another vector to define it. It will be required when r is greater than 3. It will be required over there. And here I am counting storing the x value, and v and this is the matrix of v at vx and vf. And here these are the plotting things. Okay, so here just remember that what I have to plot, I have to plot the functions. And so I will not go over the detailed code. I will share it. If you have doubt, you can ask me about this code. I am just simply plotting the functions and the straight lines. And these are just these things I have used to just to join the straight lines. Just very simple thing. And yeah, so this is the code. Okay, so this is the straight line. This is the xn plus 1. This is my phi of xn, right? And here at x equal to 0.8 I am starting over here. So 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 here this is so I haven't drawn the first initial line, so I should have drawn that. So you can modify the code and do it that. So first it will go from here, then it will come down, and this like this. So it is, so generally it is starting from here, from the straight line x0, then it is coming down. Let me use another color. Then it is coming down to my this curve. Then again it goes to the straight line. This is my, it will give me my x1, my first initial case. Again it will come down. You can see that after here it can come down here, then go here, then go here, then like this. So it will converge to x star equal to 0 point. Because what we have found that, so it is exactly agreeing with theory, because at when r is less than 0, the solution will converge to this point, because at 5 prime 0 it is equal to r, and this is 0.8, and this solution is greater than 0.8, greater than 1. So obviously this solution will converge to this point. So this way you can very easily verify you can find the convergence criteria based on this kind of plotting. So this is known as Cobweb plot. Okay, so what is happening? So I'm starting from here, going down to this, then I am going to the function, and consequently it is converging to my solution. Now this is the second one, is for r equal to 1.7. So here my 5 prime, remember that 5 prime 0 equal to r, and 5 prime of another solution is probably 1 minus 1 over r is equal to 2 minus r. So at 1.7, this is not the stable, but the solution will not go to this solution. Solution will go to the move to this solution. Again, I am using the same code with same initial guess, but at different values of r. Just go through the code, and here you see that the solution, that the diagram completely changes. Okay, because it will converge to this root. This is one root, this is another. It will converge to this root. It is again starting from x equal to 0.8. It is coming down, then again move to the straight line, go up, straight line, up, and then it converges to this point. Okay, now Now if you so I haven't done it, so I have mistakenly write it for article to 3.2. Now if you use 2.3 or 2.5 or any point, you will see a similar kind of diagram, exactly similar kind of diagram. It will converge to this point. It is 1 minus 1 over r. Okay, this is for, so you will find that this is the another root. So in 2.5 it will be 1 minus 1 2.5, so it will be 0.6. You will see that, wherever you start the solution, it will always go to this point, not in this point. Okay, now so this is not for r equal to 2.3, it is r equal to 3.2 actually. So now when it is beyond 3, okay, then many interesting things happen. Again, I am using the same thing, same code. Only difference is here the solution will not match. Yes, Shom.
Therefore, greater than 3,
Hmm.
like 3.2, it will be 2-point stability, right?
It will be 2 point stability, right? Yes, it will be 2 point stability, right? So if you here, so here you see that previously I was using this. Here, as the solution doesn't converge, here I have to modify it a little. So it is, I am taking up to some point where I want to stop. Just L equal to take 10, 100,000. L is just similar to your number of iteration, and that means how many values you want to take. If you don't do this, then then you will find some error in your problem. Okay, so here I am just modifying this. So here VV is V, it is taking a value up to this 1 to L, okay, up to 1 to 1000. And other part of the code is the same. So here you are right. So you are getting a 2 point stability. It will just rotate like this. It will just do this kind of rotation. Similarly, if you increase your r far little further, you will get a 4 point. You will get a 4 point of something like this and something like this. 4 point stability, 8 point stability. It will go like this. Now, when you take the value again higher, 3.8, then you will find that there is no stable solution in your problem, and you will see something like this, some chaotic behavior you will observe. All of these things coming from this simple equation. So in this way, for any kind of function, you can find a convergence criteria. You can modify it, just modify it to find for xn plus 1 equal to sine of xn. You can do that. Just in that case, just change the code here, and rest of the thing will work similarly. Okay. Okay, so let me start recording again. So I think it will be better if I tell you about the detail of the code a little, then it will be easier for you to understand. So let me start with a fresh one. Yeah, so this one is fresh. So here I am defining the value of r. So I should have comment. So from the next time I will comment every section. So so then it will be easier for you to understand. So here I am defining r. This is the value of 1.7. So G and VB are some function, it will be defined later. Here this func is I am defining the function as func, and this is my initial value of this is phi of x naught. Okay, func of x0. So this is the standard tolerance convergence thing, and this is where I am doing my iteration process. Okay, so this is so you can modify this equation accordingly. So here I am mainly, so this is the thing, that phi of xn. So this is basically what I am doing over here. Okay, I have done it by some complicated, but you can do it very simply. Just update the value of x and store it. This is the basic idea for that. And here I am storing the value of x. This is, yeah, so this is where I am storing the value of x, vv, at the vx1 to end. That means when this loop stop, and it will indicate the end. So this is where I am defining the vv. I will come to this, why I have commented this. So here, and v equal to vx comma vf. So I am defining this value. So this is the vf, this is the vx. So again I am defining it in another matrix, which is v. So here, this is, I am just plotting defining the function for this point. So here I am just plotting this and this. Here x plot, f g plot is just x plot I, same. So this x plot f plot will draw the parabola, and x plot g plot will just draw the straight line. Okay, just change it to x plot. Okay, the same thing. So hold on, and here I am now drawing the straight line. Okay, so how I started, I have started from here, then come down here, then go up here. So there will be two kind of straight line, one which is joining this and this, and another straight line which is joining this and that. Okay, so so this is for this two. One is for joining these two, and another is joining this two. So you will understand. And to plot a straight line, you just need 2 points and here these two are the x points, these two are the y points, and just if you just do plot, the MATLAB will draw the line for you. Okay, if you just provide it to x value, x1, x2, y1, y2, MATLAB will draw a line for you. Okay, and here this is the same thing, and just give the label and you will see your plot over here. Now in what I am doing over here, in this part here, see, when r is greater than 3, this solution will not converge. Okay, so I am taking some arbitrary value. Yeah, so this is my similar to my max iter, maximum number of iteration. As the solution will not converge, then I am defining this thing. Probably this thing will also work, vx into 1 to end, because end will be anyway 1000 there, most probably. Other, if it is not agreeing, then go over, just uncomment this, and you will get the value. So here you can modify L. So modify L to 10, 50, 100. Okay, if you just write in, then it will take you 1000 point here. But if you just plotting just to verify if it is converging or not, you don't need to go to the 1000 times the iteration. Okay, just you can define your L something like 50 maybe, and you take the first 50 values of x of your x and if x and phi x, and then the thing will work properly. So here I have taken my L to be 1000. So this is probably for 3.2. Yeah, so here I have taken my L to be 1000, and I am getting this plot. It is just a 2-point stability. So, and here for r equal to 3.8, here you can see I have taken my L only 10, because I only need to see if it is converging or not. there for that I get this kind of chaotic behavior. If you increase your value of L, then you will see many more line over it, and you will not be probably able to see anything, just a black shade over it. Okay, I have tested that for 1000. I just saw some black shade, just something dark black. So I reduced the value of L, and it was giving me only 10, or probably 10 11 lines, so I can see what is happening over there. So this is the idea. Okay, now we will, so you can, I will share the code with you, and you can try it. You can change it with other function. You can play with the value of r. So one function can be r into sine of xn. You can try it. Probably you will see similar kind of behavior. I'm not sure. You can play with it. Just change the function name. Yes, Shom.
Sir, any function containing single hump structure will show similar properties.
So we will see similar properties now.
Yes, for any function showing a single hump like
Acha,
structure.
yeah. I have also read that somewhere. Right. So you will probably see similar kind of properties. So just play with the code. Okay. So now another interesting thing. So it is, so in the first in the first interaction. So we are dealing with dealing with f0. So f0. So you see that f0 is similar to, so f0 is the inbuilt solver in MATLAB to find a solution for the nonlinear function. So there I have to provide my initial guess and the function corresponding to that fx. Okay, then f0 will work just like the Newton-Raphson thing. So there we have encountered one problem to find the solution of x to the power 4 plus, no, not x to the power 4, x to the power 4 minus 1 equal to 0. So we tried to solve that problem. Then there I have shown that from the from this RDZ, from this RDZ or IMZ plot, that if you start if you are in this plane somewhere, then your solution, you have four solutions. This these four are your solution. Then your solution, that it is not trivial. From if you start from one point, then it will always go to this point. It can also go to that point. Or if you start from here, it can come to this point or go to this point. There probably someone asked a question. I have told them that it is not guaranteed that if I take some initial guess, if I take the initial guess here, it will always go to this point, not that point. It is not guaranteed. Okay. So here, from this plotting, so first let me tell what I am doing. So I want to verify this behavior. If I start from one point, where it goes, and I want to do it for my entire plane. Okay, this is my RE axis, this is my IM axis. I want to do this for entire plane and see what happens. So this is the basic idea. So let me just erase this. Right. So I want to find a solution of x cube plus 1 equal to 0. So it has three roots, we know that. One is minus 1, another so it is my minus 1, another will be this, something like that. If I am this plane. So some one real root and two imaginary roots. We know that. One omega and omega square. So here my idea is to take the entire xy plane. Okay. Now to do that, so here this is my range of that. So minus 2 to 0.01 to 2. So I will take the value up to this range. Okay. This is my minimum, this is my maximum, and this is my delta x. It is step size. Similarly, in case of y, I am also taking this. Here I have used a command called mesh grid. It will create a matrix for you. Okay. So what is the basic idea? So just think physically. So at this point, suppose this value is 3, 2. Here it will be 4, 2. Here it will be 5, 2. Similarly, it will be minus 2, 2. Similarly, we count in this way. So if I have dots all over the place, I will find a number in that sense. Right? 3, 2, 4, 2. Similarly, it may be minus 10 comma 2, something like that in this thing. Mesh grid helps you to do that. Mesh grid will create two separate matrix for you. Okay, one matrix will be in the x domain. So here you will find that the all in one case we will find that all rows are same. Suppose minus 10, minus 10, minus 10, minus 9, minus 9, minus 9, and similarly in this case it will be minus 10, minus 9, minus 8 dot dot, again minus 10, minus 9, minus 8. So in one case all the rows will be same, in one case all the columns will be same. It can be vice versa. In x or x, I have forgotten that. Just try it. So in basic idea, mesh grid helps to generate how we read all the points. Mesh grid helps you to build that. Okay, it gives you two separate matrix, and and now when I am using this thing, so in the why do I need mesh grid? Mesh grid I need because of this. I want the value at each point. Okay, because I want to take initial guess for all these points. Okay, so this is an imaginary plane. So it will be 3 plus 2y, 4 plus 2y. Okay, so I need the x and y value for all of these points. You can build it. You can do it using a for loop. It you can do that. Okay, but here we can just do it using one line of comment. This is mesh grid, and here I am defining my z equal to x plus 1i. 1i is the imaginary I times x. Y. Okay, so I will get a matrix. I will get a matrix of this kind of these initial conditions, of these initial guesses. Okay, 3 plus 2y, 4 plus 5y, 6 plus 7i, similar something like that. Okay, now I will. So what is the idea? So there is one thing which is called image SC. So if you just Google what is image SC, suppose you have a matrix. Okay, it was 1, 2, 3, 4, 5, 6, 7, 8, 9. If you have a matrix like this, if you suppose this is A, if you just do image SC of A, image SC will assign a color. It will basically generate a plot based on your matrix. Okay, and for one, suppose it will define blue. Suppose it will define this orange color. For two, it will define this greenish blue color. Okay, for three, it will define this purple color. So based on your value in your each cell, it will define a color. This is what is images. Okay, this is very interesting thing. Again, for this something like that. So you will get a colorful. So you will get an colored image of your matrix. Okay, so this is what is image SC. Now for this initial guess, now what I am doing. So there are couple of this is a little complicated code. So I will go very slowly over it. Okay, so how to solve? The base idea is to solve the Newton-Raphson technique. Okay, other things are just the graphics modification. The main thing is to solve the Newton-Raphson. Okay, now what is this? So angle, first of all angle. So here z is a complex number. If you write the angle of z, it will give you the corresponding angle. Okay, so this is y, this is x, this is y. Suppose this is theta. It will give you theta equal to tan inverse y by x. So this is basically the angle in radian. Okay, so here I am defining it like this: angle z plus pi by 3 comma 2 pi. So mod is it will give you the remainder. We will give you the remainder of the this division, and I am dividing with it a 2 pi by 3. And this, and then I am using cell. ACIL means the ceiling. Okay, suppose you have a value like 0.3. If you use CEIL, it will give you the value of 1.0. If you again seal is 1.7, it will give you the value of 2. Corresponding to it, there is another thing which is called floor. Floor of 0.3 will be 0. Floor of 1.7 will be 1. Okay, this is just like your house. At the top there is a ceiling, at the bottom there is a floor. If there is a number in between, if you use ceiling, it will go to the top. If you use floor, it will go to the bottom. Some just basic idea. So I am doing that here. So basically it will give me 3 different values. Okay, if you do that, calculate it, it will always give you 3 different values. Okay, it is designed in that manner. So probably 0, 1, 2, most probably 0, 1, 2, these 3 are the values you will get, or 0, -1, 1, something like that. Just test it. Then images, see, I am doing now. I will just plot the image. Now when I haven't started my iteration, I will get a picture like this. Suppose this is my graph sheet, this is my plot sheet. I will get 3 distinct regions. This part will be blue, this part will be yellow, and this part will be this greenish color. Why? Because I am using images C, and in the matrix I only have 3 different values. Okay, see, if here Z is a matrix, similarly angle of Z will also be a matrix. Okay, and I am modifying the value in the cell using this ceiling command. I am modifying the value of the inside the cell, and it will be 3 different values. So Matlab will assign, images will assign 3 different colors, right? Now I am using Newton Raphson over it. So what will happen after? So after the iteration, the value at each cell will change. So here, what is the code? This very simple code. Okay. So I have started with x cube plus 1, but I have finished with solving x cube minus 1. Same thing. So here this is z cube minus 1. So this is the function I was using. Z cube minus 1 by 3z squared z. So what will happen? So so we know that so suppose I am starting at this point. Let me use a different color now. Suppose I am starting at this point. Yeah. So I don't know what will be the solution. It has 3 different fates. Okay. So these 3 are the solution lines, right? It can either acquire the color white, yellow, which is close to this thing. It can acquire the color blue or this green. Okay, but that means its value is changing from this thing, and the solution can go to either of these 3 routes. Okay, so its value can be changed. Its value can be changed to either 1 or omega square, right? And after changing, I am using this command. See that it is inside the loop. So I am always modifying its value to either 0, 1, 2 using this command. So its value can only vary between 0 and 1 and 2, and I am just plotting it. And after doing that, you will see this kind of plot. Okay, here you see that here all the solutions went to this value, yellow value. So this is the non-triviality. here all the value going to the value, but beside that there are some these values, goes to the green region. Okay. I'm not sure, maybe this is maybe 0, this is 1, this is 2. Okay, you can assume it that this value corresponding to the z equal to 0, this is z equal to omega, this is omega square. This is just, I'm just telling you the arbitrary guesses, arbitrary number. Okay, so this indicates that this solution goes to this omega square, but here just beside that this solution goes to z equal to 0, and this solution goes to z equal to omega. Similarly here, similarly here. So this thing, and one interesting thing you can see, these patterns. So this is one kind of pattern, right? Here so here I am using this resolution. So this will indicate resolution. If you improve your resolution, suppose -2 colon 0.0001 to 2, you will get a very high resolution image of it. This is not a very high resolution image. If you do that, so I will send you a high resolution image of that. So using an increased step size, you will. But one thing we can see that this thing is just copy of this thing, copy of this thing. So these things that are copying each other. So this is called fractal. And this whole thing that you are getting, it is called a Newton's fractal, because we are getting it from the Newton-Raphson technique. So the basic idea is that, so basic idea where we have started, that you have no guarantee if you take initial guess where it is going to converge. This is the basic idea. I am starting from this, I will get one solution, but just beside it I am completely getting a completely different solution. It is not, it depends on your initial guess and you cannot be sure. But if you are in this region, you see that value doesn't change. So it indicates that if I start from here, it will again ending up in this solution. Okay. Similarly, in this thing, there is no interesting thing, no interesting thing. Only near. So just let me erase everything over here. Delete. So this is one solution line. This is one solution. So these three are the solution line, right? Here. So we draw in this manner, right? So only near this region, the interesting things are happening. Here, again here. But if we are going away from it, it is a straightforward thing. If we start from there, we are ending up there. So all this thing is generated using this simple Newton-Raphson technique and two lines of complicated program. Okay. So this thing, you can modify it as you wish. Okay. So you can just, if you wish, you can just take, so you can try it. Just you can do something like that. One thing, that ImageSC doesn't work on the complex function. Okay, so this is the main problem. So you cannot just write ImageSC of Z. You have to write at least something ImageSC of AB of absolute Z or something like that. If you use absolute Z, you will find concentric circles like that. Okay. So because absolute of Z will indicates a radius in the two-dimensional plane, square root of x squared plus y squared, this is radius. So you will see something like that. But after you use this thing, you will see similar kind of pattern. Similar kind of pattern like this. You will be able to see that. If you find it complicated to grasp this thing, you can try with ABS of Z, that is the absolute value of Z, and finally you will see this kind of image. Now let's solve this problem. So this is for z cube minus 1 equal to 0. Now what will happen for x to the power 4 plus 1? So just a moment, let me just start my recording again. So I will post the high resolution image for this z cube plus 1 and for this z to the power 4 minus x to the power 4 minus 1. So you will find in the in my Google Drive. Right. Okay. Again, the code is exactly same. There is no difference in the code. Here for the x to the power 4 plus 1, we have 4 different solutions. Similarly, you can try it for x to the power 4 minus 1 as well. You will get 4 distinct solution. So what will be the solution in this case? It will be, I think, x square whole square minus I square, I think, equal to 0. So x square minus I, x square plus I. This is the solution. And here it will be x equal to plus minus of root I. And it similarly something in this case. So you have to factorize it and solve it. So we can find the roots analytically in this case. All 4 complex roots. Now let's solve it using the Newton-Raphson technique. Again the same thing, only this thing I have changed because here the difference will be pi by 2 because I am dealing with this I thing, x square plus I, x square minus I. It will be so the difference will be in the pi by 2. So I have modified it this accordingly. Previously I have used pi by 3 because the solution lines are this. The difference of this 2 pi by 3. I have used that. So now here I have used that pi by 2. Okay, there will be 4 roots. Again the same thing, ceiling. Just a moment. So I am using the Newton-Raphson formula Fz equal to z minus Zn plus 1 equal to Zn minus of f Zn by f prime of Zn. Okay. So here f of Zn is z into the of Zn is 4Zn cube. So I hope that you understand the meaning of this. So here it is using the previous value of z, and here it is updating it, and it is doing it again and again. Okay. Okay. Let me share my let me share my this screen. Just a second. I want to show you what is the meaning of CEIL, the ceiling comment. So I hope you can I hope you can share this screen. See the screen. See that the CEIL will let you go towards the positive infinity. So like I have told that if you have floor, it just consider your room. If you have floor and if you have your ceiling, and your number is in between this floor and ceiling, this ceiling will push you up. So here the CEIL of minus 1.9, it will give 1.9, it will become minus 1. Okay, here this is, if this is minus 0.2. Okay, so what is happening? 0.9, 0.2, 0.4. Okay, so this for the matrix. Okay, for the so this minus 0.2, it will be 0, and 3.4, it is obvious, this is 4. Okay, so again in case of minus 1.9, it will go to the it will push you up, that means it will become minus 1. In case of 5.6, it will become 7. In case of 7, it will be 7, but if you put 7.01, it will be 8. Okay, and in case of it can be applied. So in case of this complex number, it will be 3 plus 4i. Okay, so this is the basic idea for the CEIL. All right, so let's okay, so we can also see the images C as well. Images C. Right. Yeah, like I have told that if you have a matrix like it, the images C will assign color to each of this. Okay, you can see that this is a 1, 2, 3, 4, 4 cross theme. It has how many rows? 3 rows and 4 columns. And images C act accordingly. Okay, it has either assigned color to the images, and we are just playing with it using the Newton rapsons. Similarly, you can change the color bar, okay, if you wish. So here I have used the default color, but you can change the color bar as well and modify it using, you just Google it and you will be able to find. Okay, so let me go back to my tab, just a second. Okay, so here I am using this, and updating the value at the each step. Okay, so so let's just okay, just 1 second. Just also let me find what will be the solution of this, analytical solution of this. So z to the power 4 plus 1 equal to 0. Solution. Just a second. Yeah. So here the roots will be plus minus of square root of pi and plus minus square root of minus sign, and you need to write e to the power I pi by 2 and modify it accordingly. Okay, so these 4 will be the solutions, and this will be your final plot. So what is happening here, as I have, so here I have 4 different colors as 4 different roots. Okay, so here you will have 4 different colors corresponding to 4 different roots, and I using this image sc comment, I am getting I am getting this value, and I am then modifying it using this formula. Okay, and you will see the again same non-trivial behavior. So near these lines, you will see that some solution goes to the yellow, some solution the light yellow, this is the some solution goes to the dark yellow, again some goes to here, some goes to there. This is completely non-trivial, and it is again the self-repeating pattern. So this pattern is a smaller version of this, again this is smaller version of this, and so on. So if you increase your domain, you will see that it is continuously happening. It is never stopping around around these lines. Okay, so this around this line you will see continuously this kind of patterns, and it is getting smaller and smaller and smaller. So you can increase your domain size to see that. You will see that that this is true, that this is happening. Okay, similarly on this axis, this from here it is going to this part, here this is going to this part, it is going to this part, and here there is some I not sure if you're able to see, there are some bluish part, it is going there. Okay, and same thing is happening for other 2 parts as well. So you can modify it, try it for other codes as well. So z to the power just write z to the power 8 minus 1 equal to 0, z to the power 6 minus 1 equal to 0, you will see that similar kind of pattern will coming. For z to the power minus 6, there will be 6 roots. So I think probably you will get not like this. So this, you will get something in this z to the power minus 8. So something roots like this, 8 different colors and something like that. Okay, so again, this is known, you can, if you are interested, you can search in Google and just search what is Newton fractal, and it is, we can generate it using the using the Newton Raphson technique. And yeah, so that's all I have planned for today. If you have any doubt, you can ask me now. Yes, Shom.
So like you are using formulas like uh, x cube minus 1 and solving that. What if I use some different complex formulas or equations which have complex roots?
It will, if it has multiple roots, complex root, it will generate similar kind of thing, most probably. I'm not sure. You can try it, but yeah, so I think it will work. You can you try and tell me in the next session. I haven't also checked that. I have always used this kind of simple functions. So z to the power 8 minus some simple roots, I have always used something like that. You can try it, definitely you can try it. I have never tested that, but I think they will generate something. But this is verified that, I mean, there obviously will be non-trivial behavior, obviously. But but these solutions that I have seen, that they create this kind of beautiful pattern. If you will get a similar pattern, a nice pattern like that I am not sure, but you will obviously get something. You can try that.
Okay, sir, I will definitely.
Hmm, hmm, hmm. So what I will do, I will share this code with you, and you can verify it. Okay. Okay. So
Y-
that's
Yes, sir.
okay. Okay. So if you don't have any questions, then we can leave, and we will meet in the next week. Okay. Okay. Thank you.
Thank you, sir.